Everybody close your eyes. Close your eyes. Everybody close your eyes. Jackie, you too. Close your eyes. Brittany, close your eyes. Let's see. If you're in the room, go ahead and close your eyes. Stop for just a second and imagine where you might be in, for those that are still in high school or continuing their education. Imagine where you might be in 10 years, 15 years, what you might be doing. Hopefully you've thought about this or are thinking about it. Jackie, think about where you were when you thought about where you wanted to be in 10 years.
I never snapped at you.
Okay, open your eyes. My official title is I'm the Vice President of Academic Affairs at the Raggio Research Institute, right? How many of you just thought that when you get into your career, you want to be an administrator? No, it didn't happen, did it? Neither did I. So what I'm going to tell you about today is why I actually am in administration, but I'm going to tell you a little bit more about my background that does not relate to administration. Jackie, did you think you were going to be going into administration? Was that what you picked? No. Okay. I'm going to tell you about what I thought and what I saw and what I wanted to do. So, just like these kids, I was imagining something beyond being an administrator, wearing a suit and tie and being an administrator. I was imagining something else. But at that age, I wasn't ever actually imagining what I wanted to do in my career, and which I've done and am doing. So the purpose of this short presentation to begin is I'm going to familiarize you with my background and technical expertise, not as it relates to administration, although it does relate to administration a little bit. And then just basically share some of the things I do about things I do in my career. Okay, who's heard of Wordle? Yeah, Wordle. I use Wordle. That's my CV right there. That's my Wordle. Anybody want to know what Wordle is? If you haven't, just cut and paste into Wordle, W-R-D-L-E, put a document in there. If you want to actually get some meaning out of a document by the number of times the word's used or something, put it up in there and it makes this graphic for the document for you. So it can sometimes help you in your writing if you ever really want to say, am I conveying some of the major themes within that, just from the words being used. Anyway, that's Wordle, that's my CV, that's my curriculum vitae, that's my resume, all done in Wordle. So that's my name. I'm a doctor, publications, ecology, Antarctica, Nevada University, etc. So you'll be able to see some of what makes up my career. I'm going to talk to you a little bit about my background. My education started before I knew my education ever started, and yours did too. I'm going to tell you a little bit about the background where I came from. There's some pictures up there that help me tell the story. I grew up in western Montana on a small farm, and I raised calves when I was in 4-H. And a lot of what I learned when I was raising calves would later translate to what I do with krill and other things, as I was learning that I needed to provide them energy. I needed to provide them with an environment that didn't take more energy than I was giving them, so they could grow and they'd get fat and they'd get healthy and stay healthy. Okay? This was when I was on a farm and I was about this tall, and I was doing that. What was I learning about? I was learning about energetics. I was learning, and that was part of my education before my education actually I know was even started. My parents, well, we were farmers. My dad was also a mechanic, and my mom was an accounting assistant. And being a farmer and an accounting assistant in western Montana, and this is a picture that reminds me of my mom and dad when they would sit around the table at the end of the month and they would talk about finances. As you can imagine, in western Montana on a small farm and being a mechanic, you really had to pay attention to the bottom dollar of how you're going to get things done. So my education also involved being able to learn about finances and how to put together your finances so you can get something done with what you have, living within your means. You guys maybe have heard about this, right? I'm not sure if you're this age. You guys get the lecture from your mom and dad or somebody about living within your means, turning things out. Anyway, that's part of my background that I take with me and is helping me in my job as a scientist and as an administrator throughout the time. Another thing is, I put this picture up here, is that in the community where I grew up, there was a wealth of knowledge from the people who had been there and done that. Meaning that we learned from people not through books, but through word of mouth and through community about, okay, what's happening right now in terms of like, okay, when are we gonna harvest? Are you gonna harvest this week? How are you doing this? How are you doing that? When are you gonna harvest? You know, what's the best practices for being a farmer? Where did that all happen? A lot of it happened right here in this place called the Coffee Cup Cafe. Okay? It happens in a social setting. A social setting was the way that information flowed in and around that community. It wasn't by books. It wasn't by you know, the internet at that time. It was by communication and social setting. A lot of that actually is the way that you guys are learning now too, and that we're all learning. We're learning through social setting, and that plays a big role in the way that information flows and people get educated in this day and age as well. It's not actually any different than it was before. People will tell you it's different. Yeah, the modes are different. But guess what? Education still happened that way back then too. Okay? Okay. I grew up a place called Bitter Valley. River runs through it. Is actually somewhat true to what I did back in Montana. I actually grew up fly fishing too. I ended up fishing on the Bitter Valley, not far from where actually the book was written. Anybody ever hear River Runs Through It or watch a movie? It's a decent movie about fly fishing, brothers and family. But I did grow up fly fishing. Okay? That laid the groundwork, because when you're fly fishing and you're learning about how fish will be attracted to their food, and you have to copy their food, and you have to know how the water moves and all these other things. I didn't know it, but that was also part of my education, because that then laid the groundwork for me trying to understand life histories of bugs, trout, fluid movement, temperature, all these things that come into play in order for you to be able to be successful in fly fishing. Okay? Didn't know that, but that was part of my education. Okay. All of that is happening before I really knew what I was going to do in my life. When I was 12 years old, I read a book. It's called Shark Stories. Valerie and Ron Taylor. That's why the picture of the sharks are a big great white shark, right? Written by Valerie and Ron Taylor. I read a book about that thick, and it's called Shark Stories. I'm in western Montana, growing up on a farm, raising cattle. And at 12 years old, I decided I was going to be an oceanographer and marine biologist. I'd never even seen the ocean. Kind of crazy, huh? I'm a little bit crazy. Some people, I heard the comment, you said, marine biology would be kind of cool, right? Yeah? Anybody ever thought about marine biology, oceanography? Yeah? I did. Never been on the ocean, never know anything about the ocean, except for what I've read. But that right there was actually the time when I can look back in my life and I said, this is what I want to do. Some people may be there and some people may not be there. Anyways, it was that time. For whatever reason, that's it. First generation college student. I went to Montana State University. And I went to Montana State University in Bozeman, Montana. And I put the Bruce Jenner up here. He's a decathlete, an old decathlete. Who's ever heard of Bruce Jenner? You guys have heard of Bruce Jenner? Really? All right. Okay. There's only a couple people in. Anyways, he was a decathlete at the time. I went on a track scholarship as a decathlete to Montana State University. Before I got that scholarship, I was looking to go to Montana State University. Actually, I applied to go get a scholarship through the Navy, and I was rejected because I had asthma. They wouldn't let me into the Naval Academy. I tried to get in. But I settled, and because I had asthma, I was a decathlete anyway, so I went to Montana State University on a scholarship. So that's what led me into Montana State, which was where I was a decathlete, I studied in a forestry lab, I studied in a veterinary lab and ag experiment station, but I didn't actually study. I just got a part-time job there because I needed money to go to school. The decathlete scholarship was only partial scholarship. Anybody that goes into track or gets a scholarship in tracks these days, they're never full scholarships, so only partial. So we've got decathlete, vet lab. I was working on viruses. I raised sheep. I raised lambs. It was actually a little bit of a sad story. Working in a vet lab, it's always a sad story. Anybody ever worked in a vet lab or want to work in a vet lab? It's kind of a sad story. You raise the sheep in there so they can be experimented on. So I didn't like that too much. But from what they found was actually pretty profound because it was the virus that caused intestinal diseases, and they actually found a good vaccine for it. So that experimentation actually helped out the sheep. Is that what I wanted to do to become a marine biologist? No. It's just I laid out a path for how I was going to get into a general biology degree and get that degree and then move on to oceanography and marine biology as best I can later. Still have my sights on doing that. Okay, so I was doing decathlon. Took a class from a guy named Denny Lee. I'll remember it forever. It's a great class. He was the professor that I learned actually ABCs, called activity before content. It's the first time I knew this, but basically he taught me that we basically, and he would come in and we'd do these demonstrations and everything's going on. He had bowling balls and feathers falling and everything, and it's demonstrating gravity. But he was also the person who impressed upon me that we do not know what gravity is. The definition of gravity right now, still to this day as we know it, is the Earth sucks. Right? It sucks and it pulls things to it. That's gravity. Explain it better. We know what it does. We just don't know exactly what it is. Physicists taught me this. It's like, okay, put it pretty simply. We don't know a lot of things. Taught me that the Earth sucks, and that was pretty cool. I took a class of virology. I never really was drinking coffee until I took this class, and it was 8 o'clock in the morning class, and this guy stuttered. It was 8 o'clock in the morning, he stuttered, I could barely stay awake, so I started drinking coffee then, and I never turned back. I drank tons of coffee. I played rugby. I switched from decathlon, and I got into a rugby club, and the coach of the rugby club studied an algae called Amphora coffeiformis, a very tiny microscopic algae that adheres to is an algae that adheres to rocks. So who walks across a stream and you slip, right? And you walk across a stream. That's the diatoms and the slippery algae on the rocks. And he was studying this. So the coach got me into studying amphora. And I got to work in his lab. While I was going to school, I actually would find a way to put myself through school. I fought fires during the off seasons, and so I have enough money to get me through and pay my tuition and make my way through college. So, amphora, fire, and let's see. Okay. Because of my work or my connection to my rugby coach, he knew somebody that wanted to work on how diatoms, or these algae, adhere to ice crystals at University of Southern California. Fight on Trojans, right? Who's USC fans? Yeah, all right, fight on. So I went to USC. How can a student that grew up on a farm in western Montana had to work their way every year all the way through school in Montana paying in-state tuition and residency? How can a student like that go to one of the most expensive private schools in the nation for their graduate program? Anybody guess? Anybody know? Venture guess. Throw something out there. Student loans. Yeah, just go in debt, right? Yeah, there's a guess. Anybody else? What's that? They paid you to do it. How many people know that? that when you go to graduate school, they pay you to go to school. You can get research assistantships. This is the path that I figured out, and I did not know this, is that you, when you're going as an undergrad, most of the time you're paying the tuition, and you're paying, and you're getting scholarships and all this other stuff. But when you go to graduate school, there is a path forward. You don't go and pay your tuition. By and large, you go and get admitted to a graduate program, and you find somebody, and you work in their lab, and they pay you a tuition, or not a tuition, but a stipend, and they pay your tuition. It's not the only way to do it, but it is by and large a large majority. So if you're thinking about going to school and you think about graduate school as a big barrier to what you want to do in life and for going into science, think about undergrad, but graduate school is, there's a myriad of ways to go do it. You're not going to get rich, but you don't have to go in debt in a lot of the professions you go into. Not all. There's some that you will go in debt. Who wants to be a chiropractor? If you want to be a chiropractor, you're going to go in debt because they don't pay you to go to school. You have to pay them. Am I right? I mean, there's other ones that you're going to go in debt. Med school, you're probably going to go in debt. There's a lot of other ones. But if you're going into something like I went into, they admitted me into the program. They paid me a stipend. They paid my tuition. And then I went to school at USC for 4.5 years. And I took out some loans too, but not too much, okay? I took out loans because I had a child. I needed support more than just me. Anyway, okay. What did I do at University of Southern California? Real quick. I started my studies in oceanography. I went to USC, I was an oceanographer. I'm from Montana, I'm an oceanographer. I got picked to go to Antarctica with, actually my advisor didn't even go, he just sent me to Antarctica. And it was really, he told me what the expedition was, and it's like, okay, you get to go with 15 US scientists and 17 Russians. I was like, okay, where are we going? He said, the middle of the Weddell Sea, or the middle of the Antarctic Ocean, which this is the logo from where we're at. And who's ever heard of Shackleton? You know, the Shackleton story. Shackleton tried to get to the South Pole and got beset in sea ice, and his ship got crushed and it sank. And they floated around on ice for a while, okay? We were going right to where his ship sank. And they put us off the ship, and then the ship sailed away. It said, see ya. And so we got to live on the ice, the floating sea ice on the ocean, and do the work that we were doing, which was work on algae that lives in ice. So I got to work at Ice Station Weddell, which was a joint U.S.-Russian program. That happened right as the Soviet Union crumbled, actually, and the Berlin Wall, or the big wall came down. Pictures of sea ice in the background. I got to work on things that live inside the ice and how they live inside the ice. And those things being algae, plants, microscopic plants. Although they're not microscopic in this picture. This is a picture of one of the Russian divers actually diving beneath the ice in these big flowing, billowing forms of algae, kind of like kelp, but they're actually just strands of slimy ones coming down underneath the ice. We studied how they grew, how much they grew, and then he studied how much the krill were feeding on them. Then I went on and did a postdoc work, and I went back to Montana State, and I went back to the inland valleys of Antarctica, where I started working on lakes instead of the ocean, where there's huge ice covers, actually 3 to 6 meters deep. So meters. Okay, how much is a meter? Somebody show me like this what a meter is. Everybody, not just somebody, everybody. Show me how much a meter is, everybody. How much is a meter? Okay, meter's about that big. Everybody, participation. Come on. There we go. Okay, meter. Okay, 3 to 6 of those. So you put 3 to 6 of those together, you're 1, 2, 3. Yeah, the ice cover is as thick as this tall, this room is tall. And inside there, in the middle of Antarctica, and where it's coldest, highest, driest continent on Earth, some of this sand from around the desert blows in on top, and the solar radiation hits it and melts it way down into the ice. And it creates this little liquid water environment there. And that happens to be a place where cyanobacteria can grow. And cyanobacteria, got a few pictures here. There's pictures of, in the microscope, of cyanobacteria under autofluorescence. You're not looking at them and they're just regular bright field microscopy, but this is some of the pictures that we take using some of the microscopes we have. Who do you think funded this work? I didn't go and I didn't pay to do this. Who do you think we got to pay for this work? Any guesses? Yeah. Okay, United States and Russian government. They do fund this type of work. Okay, so it's government funded. You're right. So within the United States, what agency do you think would actually pay us to go do this type of work? Any guess? Anybody know? Agency? What's your four-letter agency that just breeds the exploration? What was it? NASA. Yep. NASA. NASA pays us to go do this work. They pay us to go figure out how life might actually live in cold, dry, radiation environments. And some of the work that I've been doing from there on forward has been funded by NASA. A lot of the work that we have published over the years has all been funded by NASA. The National Science Foundation funds us as well. So I got my job up at the Desert Research Institute. Everybody else heard of the Desert Research Institute besides the person that drives about all your TNCC? People drive by every day. Anybody else hear of it? Anybody not hear of Desert Research Institute? Okay, it's a Desert Research Institute. It's a research. It's this research labs, collection of labs up on the hill. We also have a location in Las Vegas, but it's basically we're science geeks doing science stuff on the hill. Is that a good way to explain it, Jackie?
I think it's perfect.
Okay, that's what we do. And I have a license. I have a license to be a science geek. That's my job. That's what I do. I got a lab. And what I brought some instrumentation and a bunch of other things that we might have some time to get into. But I just do whatever I can convince somebody is compelling to do and I find exciting to do. Okay? So, some of the other work that I've done is the work on dry valleys, ice. Been to Antarctica 14 times. I also do work on the Truckee River. The Truckee River grows lots of algae in it when you put nutrients in there, but one of the studies I've done goes back into figuring out how much nitrogen you can actually put into the lower Truckee River before too much algae grows, and when they die or actually respire at night like they're doing right now, they're respiring. These plants are respiring, we're all respiring. But how much oxygen they take out of the water, which would then kill the fish. Okay? I got funded big time to do that because it has so much importance. Okay? So I worked on the Truckee River, and then I've also been doing, I've been teaching a bunch of different programs. This is a list of all the students that have come through my lab, not all of them, but a whole bunch of them. And so in doing this type of work and research, they get their degrees and they move on. One guy just got a tenure track job at Georgia Tech. He has a license to be a science geek too. Another lady which came out of my lab, she went down to Stanford. She just got an assistant professor job at Colorado. She has her license to be a science geek too now too. She can do anything she wants. She has academic freedom. She can pursue and do what she wants to do because she has the skill sets to do it. She can convince somebody to pay her to do it, and that's what her job is. That's what I'm doing. Okay. NASA work. There's a little bit more of the mid-career things. NASA work. Here we are. Because of doing science that's funded by NASA and then also doing some of the other work that I've done, run a program called Space Grant for the state. I have done that for several years, and you guys might even recognize one of the pictures up here, okay? We run workforce training programs where we give funding out for people to do high altitude ballooning, taking pictures. I don't know if you got, how many people have been in a ballooning program in the Truckee Meadows? They've impacted a few number of people. If you haven't done one, you might want to do one. Do one on your own. If you do, be careful. But you can send cameras up to near outer space, get great pictures. You can do some science associated with that. You can get into sounding rockets. We funded the AACT to build a moon buggy and go compete in Alabama. That group that I was actually at the AACT, they competed against universities and they won, I think, the best lightest design. And they were competing against university teams. Okay? And I work at DRI now, Desert Research Institute. We do environmental research around the world that's improving the lives of Nevadans and anybody else across the world. We do research on every continent. We have global reach. I get, like I said, I get to do research. That's my job. So, when I close my eyes and I think back, I told you where I thought I was going to be when I was 12 years old, right? And I've learned some lessons along the way. And I've learned some tricks and also have had the opportunity to do what I thought I was going to do when I was 12 years old, and that is be an oceanographer. Been to Antarctica 14 times. 8 of those times is all doing ocean sciences work. The other part of my life, I'm just pursuing other things, aquatic life. I do work on the Pyramid Lake, I do work on the Truckee River. I do work in actually different lakes on the Antarctic continent that even have thicker ice covers. The latest one that we did is at Lake Vida, 20-meter ice cover, and beneath that there's a brine, really salty brine where there's life living off of the energy derived from the rocks. Oh, wait a second. They found the exact same type of environment on Mars as well. Very similar types of environments on Mars. We're finding life that can live there and get their energy from different means. There's a possibility that it's not that hard to live on Mars. All right, everybody point, which direction is it to Antarctica? Point, which direction is it to Antarctica? All right, get your bearings, get your bearings. Everybody point. Everybody's got a point. If you're not pointing, you just got to try it. Come on. Make a guess. Make a guess. Which way to Antarctica? Be definitive. Don't be like, okay, I think it's this way. Go. Point one direction. Go. Which way do you think? Everybody. You got a guess? That way? Okay. I don't even know. Which way's north? Everybody point north. Everybody point north. Okay, let's all agree on that's north, that's south, that's east, that's west. Okay? So north, south. So everybody point the direction to Antarctica. That way? Antarctica's in the south, right? Southern hemisphere continent sitting on the bottom of the Earth that's surrounded by an ocean. The Arctic is on the northern hemisphere, North Pole, and the Arctic is an ocean surrounded by continents. Very different. So, that way to Antarctica? Yeah, actually, there's around. I can get there. I can go across, right? Good question, right? I can go. I just got to go through the Arctic first and then go all the way around the other side. But yeah, I can get there if I go down. I can't get there if I go that way, okay? How do I get to Antarctica? Anybody? How do I get there? How do you think I get to Antarctica? I need to hear something. Yeah. Helicopter? Okay, get into Antarctica. It's a good guess. Can't walk. It is, I just gave you the answer. Can't walk. It is a continent surrounded by an ocean. How do you get over oceans? Ships. What else? What? Dogs over the ocean? No, dogs don't go over the ocean. Okay? That's how big Antarctica is, by the way. That's how big the continent is. Okay? Go to the airport. That's how you get to Antarctica. You go to the airport. You go in here and you pack up all your stuff. You go to Antarctica and you take a lot of your supplies with you. What kind of supplies do you think we take? Down jackets. You bet. You can take down jackets. What else do you think you might take? To go do research in Antarctica. What's that? What? Yeah, you got drill. We got drill right over there. Yep, we will take that. You bet. Any other guesses? Down jackets? What? Yeah? That was like an auctioneer's, like caught you waving at somebody going by. What's that?
Those things that they stick down in the ice so they can pull up forwards.
Yep. Yeah, they're called ice core barrels. These things right here. These things. Yeah. We take these. This is basically just a drill. You put it on the ice, and if I were to put it down, we'd just start screwing it into there. Core comes up in here. There's dogs. We call them ice dogs on the back end right here. Stops the core from coming back out. And then when we want to extract the core, we take the top off. In here. Take the top off, and then you just pour it out this side. Okay? Ice core barrel. This is a hand-operated one. Hand-operated little drilling rig. What else might we take besides some equipment? Yeah.
A water filter?
Yeah, you take water filters. You take. Why would we take water filters? What's that? So you can drink the water?
Oh, yeah. You don't die.
What's that?
So you don't die.
So you don't die. Actually, it's a really interesting thing in Antarctica. The reason you can't really drink most of the water around here is because there's pathogens in it from cattle and all this other stuff, right? Go to Antarctica, guess what? You're fine, you can drink the water. No problem. Pardon? You filter the salt. The salt. A lot of the places in the Antarctica that I go to, like the dry valleys, I'll show you, fresh water. Freshest water, glaciers, snow, stream flow. But yeah, you're right, especially in some salty environments, get rid of that. Okay, we definitely take boots. I'm going to just show you real quick some of this stuff. Do we take a lot of this stuff? No. We actually go fly to Christchurch, and they give us a lot of the cold weather gear that we get to use when we're in Antarctica. Because when you're going down there to do research for the government, the last thing they want you to do is go down there and be ill-prepared. They want everybody to be prepared with the types of clothing that you see here on the rack. So a lot of some of this is my material. This is my jacket, but a lot of the other clothing we just go pick it up. It's called the CDC in New Zealand, Clothing Distribution Center. How do we get out of New Zealand to Antarctica? Most often, plane, LC-130. That's an example of one of the planes. That takes, it's a long, cramped ride, 8 hours or better. You can see how cramped it is on the right-hand side. Everybody's just stuffed in on webbing, and it's really loud. Everybody has on gear on their ears so they can hear once they get off the plane. There's also, there's also a jet that makes it down in about 4.5 hours. That's luxury flying. They didn't do that in the old days. But that thing just done in 4 hours. As you can see, everybody's got their earplugs on, and they look really well rested, right? The guy on the right, he's really well rested going to Antarctica. When we get there, we go to a town. This is called McMurdo Station. Fire, doctor, a lot of the research support that we need. We have a town that sets up the infrastructure so we can get our research done. Dormitories, these brown buildings in the foreground, those are all dormitories. How do we get around? Once we get to Antarctica, helicopter. If we're doing work on the continent, so in the dry valleys. What's the name of the helicopter? Anybody? Go ahead, Blair. I don't care. What's that? It can fly. The name of it? The name of this helicopter. Anybody guess? It's written right on it. There you go, N32088. One of the things I love doing these days is teaching kindergartners about Antarctica, working on their math skills. In order to be able to fly and talk to helicopters, you've got to know your numbers. Little kindergartners love that. They just love to try to figure out what the name of helicopters are. Flying around the Antarctica valleys, that's what we do. We take lots of material to go wherever we're going. This is at Lake Biden. This is on the top of a glacier. We're taking samples out of the glacier where sediment pockets have melted down into the ice, like I explained for the ice cutters, but it also happens on the glaciers. What's the difference between a glacier and an iceberg? Anybody? Yeah. Right, yep. So we're on icebergs. What he said was, icebergs, we're on a glacier. Glaciers on land. Icebergs used to be glaciers that then have gone off into the ocean. Okay. More pictures of the Antarctic flying around in the helicopters. Royal New Zealand Air Force, we've also worked with the New Zealand Antarctic program, not just the Antarctic program. We also fly around with, on occasion, the Coast Guard when we do things over the ocean. We also get around on crampons. We're on slippery ice. There's examples of crampons over here on my boots in order to be able to get around and not slip and slide. The other way you get to Antarctica is a ship. Anybody ever heard of our icebreakers? We have 3 research icebreakers now. We have 2 research icebreakers that operate in the Antarctic. This one's called the Nathaniel B. Palmer. That ship is 310 meters long. That ship, bigger than this building, by far. The building right here, from side to side, with it's about the width of the icebreaker. That's me years ago in the port at Port Hueneme, or excuse me, not Port Hueneme, we get this Punta Arenas. We meet the ship also in Punta Arenas, Chile. It's another way to get to the Antarctic. Captain of the boat, some pictures of the ship making its way to Antarctica. It is a big ship, it breaks ice. I'm from Montana. Little did I know that when I went to Antarctica for the first time, I was going to get on a ship and I was going to go across the ocean called the Drake Passage. Anybody ever heard of the Drake Passage? It is the worst ocean on Earth. Biggest seas on Earth, besides there's another place in the North Atlantic which gets as big ocean and big waves as this. This is a critical mistake in my career choice. I did not know that I was very susceptible to seasickness. Should have figured that one out. But I did figure it out. I know how to cope with it now. I don't cope with it very well. So one thing I like to say is that if I'm going to Antarctica, I want to be on an icebreaker because I want to get there and I want to get into ice and I want to be studying ice where the ocean is perfect and smooth. It's covered by ice, the waves are all dampened, and we can get out, we can walk around, and we can do stuff on ice. There's pictures of those ships. And this picture shows when the ice breaks and it exposes what the color of the ice is most of the time in the Antarctica. It's not what you expect of ice. It's not clear, it's not blue. It's this color. It's brown. Golden brown. And it contains the algae that live inside the little fissures between the ice crystals where the salts are at. When seawater freezes, it has salt in it. But when it freezes, the salt gets concentrated in areas between the crystals and it makes habitat for where the ice algae can live. Pictures of ice being broke, ice breakers. I'm standing taking this picture on the top of the ocean. The ocean's 1,000 meters deep where I'm standing. I'm taking a picture of the ship in the foreground, and in the background, that's the icebreaker, or excuse me, icebergs. That are floating around in the middle of the Antarctic in the sea ice of where I'm working. Little ships, little boats that we're working on. I'm out sampling krill that day. I love this picture. Sorry, you guys are getting some of the same slides that I show kindergartners. I do an activity like, do you guys want to do the activities? Point out who's not on my team? No, okay. I'll spare it. We won't do that. I do a lot of international work. I work with Russians. I've already said that. I work on this particular expedition. Half of us are from the United States. The other half, they're all from Belgium. Belgium government pays for polar work as well. The Italians pay for work. Germany especially pays for a lot of oceanographic work. And the Japanese pay for a lot of the oceanographic work, especially as it relates to krill. Why would the Japanese want to really invest heavily in studying the Antarctic food web and krill? Anybody? Huh? Because what? I'm sorry, the what? Whaling. That used to be the case, but they're also just as interested in the krill fishery itself. because there's a lot of the protein of the ocean is still wrapped up in krill. Some pictures. This is some of the views that I've taken pictures of while working and standing on the ice escape of the Antarctic. Something I thought I'd share with you. When the waves do propagate through forming ice, the ice kind of hits each other and forms these round discs. And they become known as pancake ice. This is pancake ice. Those then weld into bigger pans that then become ice sheets. And that becomes the habitat. And this expanse of the ice-covered ocean of Antarctica is the same area of Antarctica itself at its maximum. We used to get around in Antarctica using sled dogs. We don't anymore. Anybody guess why we don't allow sled dogs in Antarctica anymore? Venture guess. Why wouldn't we want to take dogs to Antarctica to get around, rather than using the gas-burning snowmobiles and helicopters and things? It's because they carry distemper and other things that is actually transmissible, possibly transmissible to seals. So we've got rid of all of them on the Antarctic continent. All countries no longer take sled dogs to Antarctica. I don't know, cool looking dude, huh? Mount Erebus of Antarctica is an active volcano. Active in that the dome is still producing lava and other things. It's not blowing up, but the location of the actual Reno station is actually right over here. So thank goodness it's not that active. Oh, that's surfing. That's not Antarctica. All right. A couple pictures about what we do in Antarctica. Some of them may be redundant, some might not. Here's a picture of some of the people that I work with. It's a picture of people diving through the ice off of the ship. We get off and they just cut a hole in the ice. When I say just, we operate chainsaws and big saws and whatever, and cut through the ice, and then they go down and they'll dive for whatever we're doing underneath the ice. These are krill biologists. The guy in the middle right here, the guy right here, he's a professor at University of UC Santa Barbara. You want to study krill? Go talk to that guy. Guy's got one. He might be retiring pretty soon, but he also knows who else to talk to about studying krill in the Antarctic. There's my team. We're out getting ice cores out on the ice, doing surveys of ice thickness, snow thickness. We can determine kind of the energy balance of how much heat goes into the ice, how much it forms, how thick it'll get, and kind of what kind of habitat it is for growing algae. It's some of the tools we use when we're down there. And yeah, we're lab geeks too. We use pipettes, and we're doing chemistry of the ice back on the ship. There we are using the ice cores right over there. Some of the conditions you work out, some of it's whiteout, some of it's bluebird, sunny days. Like that. Questions? Here we are processing an ice core, taking temperature profiles and determining how much mass we have inside. And of course, every once in a while where you're out, you get visitors come along and check you out. Who's on my team, who's not, we'll pass that one up. Here we are working with the SEAL team. The SEAL is trying to track where the SEALs go during the Antarctic winter and how their diving activity is, what they do during the winter, especially if some of them are giving birth. So they put on, where is the SEAL team? They put on a transmitter that will be able to measure how deep they dive, and then they transmit that data back to satellites, and we can track them in real time, how deep they're diving and where they're sitting. Turns out that when crab-eater seals, which this one is, when they're calving, they will sit on the ice floe with the pup, and they won't eat for up to, I think it's like 2 months. And they'll waste away, and they'll lose all their mass. And then they'll start diving again later once the seal is, the pup has grown big. Pictures of working in the Antarctic night off of the ship. catching penguins. Figure out where they're going. Whoop. Figure out, they do the same thing. We put backpacks on them in order to figure out where they're going. Questions? There's a picture of one of them right there. Yeah?
How do you get the satellites to stay on their heads? Like, does it hurt them?
So it's a transmitter. There's the technique is that, especially on the birds, is that you pull up some of their feathers, and then you put basically a duct tape underneath there, and then super glue right to their feathers on the back. And no, it doesn't hurt them. Is there an extra weight there? Yeah. And eventually that will just wear off and fall off, and they lose their transmitter. Similar type thing here, but they put it on a pad that then kind of has a super glue that then just goes, sticks it on the back of their head, and then they have to swim around being pretty embarrassed for the rest of their life. Yeah.
So what happens if like elephants or runs one of the ones that you guys have had?
Transmitter usually just ends up dropping off and going down the bottom of the ocean. We don't ever get transmissions again. We don't know what happens when the transmitters go bad or they're gone. They're just gone. They only are able to actually transmit when they're on the top, sitting out, not in the water. Another question?
So when you go on these expeditions, how long are you usually there?
Okay. First time I went for 4 months. I've been, that was the first time where they just dropped us off and we were floating around. But I didn't finish that story. They dropped us off, they waved goodbye, and then they sent down, that ship called the Nathaniel B. Palmer, that big icebreaker. It had never actually touched ice, and its mission was to come get us before we floated north and the ice broke up. This was insane. I mean, this ship had never actually got out of the Louisiana shipyard and was going to come pick us up. That was the plan. Had I known, I would have been like, that's not such a good plan. Anyways, that was for 4 months. I've been down for 3 months. More typically these days, it's between 6 to 8 weeks. Fly down, do your research, come back. I work with one guy where his main job is to maintain weather stations throughout the McMurdo Dry Valleys and the whole network for the long-term ecological research program. He'll go down for 2.5 weeks. He'll go down, get his training in, pop out, get his data done. That's it. But he does it every year. So when I go down, I typically try to study processes that take a little bit, and I'm trying to do experiments, so I'm down there for a little bit longer than say somebody's just monitoring, doing monitoring work. Any other questions? No? All right. We're going to just do one other thing here. I didn't bring any algae. Algae just doesn't tend to turn people on about science. Although you can do really cool things, and algae is really cool. But slimy, smelling things just don't generally do it. I'll have to work on how to get that done. If anybody wants to try to help me out with that, let me know. Okay, one of the things that I do when I go to Antarctica is, and this is fundamental to my job, is I count photons coming from the sun. And I've got an instrument over there. It's got a fiber optic collector on there, and it's got a sensor where I can actually count the photons, characterize their energy. So I know what color, light, and the number of photons that are coming in, the number of them, and what wavelength they're at. That all makes sense to you guys, right? Everything. Okay. You guys thought that that's just stuff to teach you, okay? I live it, breathe it, do it every day. That's my job. I count photons coming in, getting reflected by the snow, because that's getting reflected by the snow isn't available for a plant to photosynthesize. Okay? So in the Antarctic, especially on the shoulder seasons of the dark of winter in Antarctica, those photons can actually do ecological work. Okay? So I count the photons. I count the photons coming in and that getting reflected by the snow. That then propagates down into the ice. That which is then absorbed by microalgae, unicellular plants, right? Unicellular plants. Plants. Okay. And then I even count further. So I say, if it gets absorbed by plants, what does that plant do with it? Does it turn it into photochemical energy by fixing carbon dioxide? That's photosynthesis, right? So a plant must do that if it absorbs it. No, not necessarily. It can do other things with it. If it's a plant, which is green because it contains what pigment? What pigments? Chlorophyll, right? If it contains chlorophyll, it's got to do photosynthesis, right? Not necessarily. You can have chlorophyll and it cannot be fixing carbon dioxide at all. So one of the other things it can do is it can dissipate that energy as heat. Are plants warm? Typically, they're typically the same temperature. Or it can also get rid of that energy as fluorescence. It can take that photon that comes in, absorb that energy, and it can shuffle it to another molecule to fix carbon dioxide. Photosynthesis creates photochemical energy, of which we all rely on that energy. Or it can pump it back out as red light. It can re-emit it at a lower energy than what it was absorbed. Red light. Can you see that red light? It's pumping it out right now. Do you believe me? I'm a scientist, you better believe me. Come on. No, actually it is. It's pumping out red light. And what we have here is, and this is actually a very transformational piece of equipment in front of you. What we used to be able to do to measure photosynthesis, we used to take radioactive carbon-14, put it in an environment where that radioactive carbon gets incorporated into the plant material. And you guys might even read about this in your textbooks. And then we quantify how much of that carbon-14 was put into this plant material. And in order to do that, I need special equipment in order to measure radioactivity. And then I have to actually generate radioactive compounds, okay? But if we can figure out where those photons go and whether or not how much red light this plant is producing, I can then calculate how much carbon dioxide is being fixed by this plant. All I got to be able to do is do that. This machine right here is able to do that. What it does. And you guys are going to be my testimonials up here. I'm going to have you read this line. It's an F-star line. It's the, okay? And this, yeah, you better turn around. This is a fiber optic cable, and all it's doing is relaying the amount of red light, okay, which is coming in a certain wavelength band, which is tuned to chlorophyll, and seeing whether or not it's coming. Ooh, hello, he said. When I'm here, speaking to the microphone. Tell them what you're seeing.
F star is starting at 0. I don't know, what does F star mean?
That's your fluorescence. How much is your cookie fluorescence?
It's good now.
300 whatever units,
Wow.
that's it.
Okay, so it is actually giving off some red light that this thing's measured. Okay?
What units is it?
Relative units, right? Okay, good question. You guys ever heard the problem, what is it, 23 plus 60 equals 1? I'm right, right? You guys ever hear that? 23 plus 60 equals 1. Come on, people. What units? 23 hours plus 60 minutes equals 1 day. Units are important. Okay, anyway, good question. Units. What's this one?
It's peaking at 1,000. 1,300. 1,400, 1,500.
Okay. So it's measuring red light. We have an instrument that's measuring the red light that is typical of photosynthetic, of chlorophyll fluorescence. What am I getting?
0. Probably because that's a fake plant, yeah.
Okay. So the fake plant didn't fool my instrument.
Yeah, it's real, I'll believe you.
Okay. So the instrument tells me this. Okay, but here's the other cool thing that I'm really excited that your cookie fluoresced. Okay. It gave off some light. Okay. But here's the other thing too, is one of the things we can do is we can gate. That's the amount that's just coming off in this light that's coming down. And I can show you what color of light, the amount of photons of light that's coming down, and you go into the spectroradiometer over there. It is nothing like sunlight. Sunlight is all across the spectrum. It is visible light from 400 to 700 nanometers. It's all colors. This looks like white light, but heck no, it is not. And I can prove it to you over there. Okay? It is nothing like sunlight. Energy that comes down hits the chlorophyll, and if it is going into photosynthesis, there's a portion of it let's see, how much, the chlorophyll molecule, if it is able to take that, here. Chlorophyll molecule absorbs that energy. And if that energy cannot go into photosynthesis, it kicks it off as fluorescence. Right? If you hit that chlorophyll molecule while it is, or it can kick off as fluorescence, or that energy can go into photosynthesis. Right? And if a lot of energy goes into photosynthesis, then the fluorescence from that molecule is actually pretty low. Because all that energy is going over to photosynthesis and not fluorescence. Does that make sense? But in order for it to go to fluorescence over here, there's a kind of a gate. All the molecules that are taking that energy from photosynthesis and going this way, if they're all busy, then this molecule can't pass its energy to this photosynthetic machinery. So then it fluoresces more. This machine measures the difference between the amount going to photosynthesis and the amount that then comes back out as fluorescence. It's called the fluorescence quantum yield. Quick little lecture. The big thing is that if I push a little button here, I'm going to get a quantum yield from your cookie. It's good. I don't know what it's going to be. I've never done a quantum yield with a cookie. What kind of cookie is this?
Chocolate.
Chocolate cookie. Fluorescent quantum yield. Your fluorescence is, when you get together and date it here, it's about 100, 200 maybe. I think if we just hit this start. Now here's the thing, is that we have to close the photosynthetic machinery by hitting it with a blast of light. Okay? So when I hit this button, it's going to give a blast of light. You might not want to look right at it, okay? It's not going to be that big. You'll see a blast of light. What's our yield right there? 0, 0, 0, y? 0. So the yield from the cookie is 0. That no energy went to photosynthesis. It all just came back as fluorescence. It's just fluorescent. Okay. Don't want to hit here. Okay, good start.
It says overflow over 3,500.
So, and the yield right here is 708 units. So what that means is that out of 1,000, so it's 0.7. So 70% of the energy that was going, that was hitting this before we hit it with a flash of light was actually going to photosynthesis and not to fluorescence. Okay. So, just a short demonstration of kind of fundamental physics that are used to study, which is actually what I do. I study how things grow, the energy and how they do it. They do it in extreme environments and with systems ecologists. That's what I do for a living. Anyway, questions? Yeah.
So would a plant like that tend to take in some of the stuff like cactus, which doesn't perhaps grow better something like that?
Good question. What do you guys think? So would a plant like this photosynthesize more? Is that the question? Photosynthesize more than perhaps a cactus? Anybody? Rationalize that, make that one out. What do you think? What do you think? I mean, what's the difference between this plant and a cactus fundamentally? Different environments they grow in. Cacti are typically really water stressed, not as much water. So when they have water, they're photosynthesizing just as much, just as efficiently than any. In fact, perhaps even more. I'm not positive of this, but perhaps even better than the ones that aren't water stressed. Because when they have water, they really have different types of adaptations to make sure that they can take advantage of that short period of time when everything's really good. So a lot of times you'll see cactus are just perfectly green and they're photosynthesizing like mad. So it depends on the environment. Good question.
So every photon that it takes in that doesn't go into photosynthesis has to be kicked off as red light.
Usually kicks off as red light. It can go into heat, but the amount that goes into heat is not it's not as favorable to go to heat as it is to just going out of fluorescence. So plants you see every day are giving off red light. You just can't see it because there's so much red light around us that we can't see it. If we could filter out all the red light that's around us and only look at the light that's coming from plants, we would see plants as being red. That instrument's set up specifically because it gates out. It only takes in the wavelengths and also the timing of which is coming from that which is being stimulated by the tip. If you actually look at the tip right now, and I didn't show you this, but if you look at the tip, it's giving off a slight amount of red light itself, or a slight amount of light, and it's giving it out in short, little, tiny pulses. I mean, milliseconds apart. But then it's only collecting the light which is coming back as a result of that pulse, and it's subtracting out everything else as red. So it does a subtraction and it does a gating. Basically, it's just some really cool engineering. We didn't have these instruments 10 years ago. They only came out about 10 years ago. It replaced the entire way that we go about studying photosynthesis. Fundamentally transforming for how we study photosynthesis across the world. Got rid of a lot of the work that we do on carbon dioxide exchange and radioactivity. I got rid of, it's actually put a couple of, it's put some people out of business on campus that used to help me move radioactive compounds around. Their business is struck way off. I used to use a lot of C14, now I don't. Because of some really cool engineering that somebody came up with. What really? Oh, question.
I'm just wondering, do we emit any red light at all?
I don't think so. I don't think so. I mean, we're absorbing photons, of course, right? But I don't think we're at any of our molecules are the kind that generate and put out heat as fluorescence. The chlorophyll molecule does that. Us, we actually generate heat. Yeah. I think that, I'm not sure. How does it make vitamin D? How does vitamin D made? I'm not sure. There's probably a cycle that helps make vitamin D. I know that that's the case with certain things. So, anyway, what are Curly? What do you think, Curly? That's what I studied. Everybody say algae. Algae. What eats krill? Whales. What else? What else eats krill? Penguins. Right? What? Vegans eat krill? They do? I don't know. Is it? It's a meat. It's protein. Okay. All right. Any other questions?
So is there any plants or things that will absorb photons and make a light that's in the visible spectrum?
Good question.
What was it?
I don't know. If they absorb the light, will they emit in the visible spectrum in plants? I don't think we have fluorescence in the visible spectrum. Well, actually, I mean, the visible spectrum is plants. Red light is invisible, but you just don't see it because it's a low amount and it's being swamped out by all the other red light that we see around. If we were actually able to block out all the red light in this room and then shine blue light on this, you would see the red from it. It's the only reason you don't see the red is because there's so many other red photons around us.
There's no plants that actually fluoresce photons coming out of
That we can actually just see them fluorescent. No. Okay, but good fundamental question is why is the plant green? Because it's not absorbing the green light. It's reflecting. All right. Yeah.
Is there like, okay, this is out there, but is that one of the reasons why we're on in chocolate? Is that
You know, I don't know why the black light. I mean, is it more photosynthetically efficient? Is it more, I don't know. I don't know why black light. Good question, I'll look that one up though. Since, because I got a really cool, have you ever been by Desert Research Institute? We have some really cool greenhouses up there, you know, I'm sure there's an industry that will pay us to learn how to do that better.
I find it ironic that you work at different research institutes and you study the seven desert. Do you go to Antarctica and you study plants?
Great question. Yeah, I study plants, but one of the deserts that I work in is called McMurdo Dry Valleys. It is actually the highest, driest, coldest place on Earth, and it is the desert of Antarctica. But Desert Research Institute is named not because we only study deserts. We actually do environmental research around the world of all sorts. We study energy. One of the projects I'm working on right now is how you can grow algae better in geothermal water in order to produce diesel. There's some people working on wind energy and other things, and it's not desert related. Yeah, good question. It is ironic. One guy came to work and he's been working there for an hour or a year, and he came to work. He's been working for an hour. He's been working for a year, but he came to DRI because he thought he loves ponds, and he thought it was really funny that he's going to work in Desert Research Institute. The acronym spells dry, so that's why he explained it. Anyway, all right, I've got instruments over there. I think I'm done for talking, but I can show you some demonstrations of the spectrophotometer if you want. I do have over on the side there, there's some tubes of little miniature baby krill that I've got, and little magnifying glasses if you want to check out krill. And I study the algae that feeds the krills, that feeds the wet. I've been doing it for a while. I've been doing it for 20 years or so. A lot of work I do does relate to climate change. I didn't talk about all the things that related to that, but that's what I do.